It's pretty wild when you think about it, like how philosophers wrestle with those big fundamental concepts, right? Like justice or consciousness, or even just the very idea of meaning itself.
Hmm. Yeah.
It reminds me of a similar kind of challenge that pops up in science, actually, specifically with what are called theoretical terms.
Interesting.
It's almost like, can we really understand the concept of something like an electron in the same way that we grasp the experience of seeing the color blue, making that leap from something we experience directly to an abstract concept?
Yeah.
It's a leap that science seems to be making all the time.
It totally is. And it's a brilliant observation. You've really hit on something that goes to the heart of what we're diving into today. The whole world of theoretical terms in science and all the philosophical twists and turns they bring with them. And we have a great guide for this journey, the Stanford Encyclopedia of Philosophy. Their entry on this very topic is packed with insights. And I know, especially with your passion for, the whole philosophy of language and meaning and how we build up our understanding of things.
Yeah.
I think you'll find how science tackles these core concepts particularly fascinating.
Definitely. I mean, as someone who spends a lot of time thinking about what words actually mean and how we construct our picture of the world, this whole idea that science has this layer of terms for things we can't directly observe. Like you mentioned electron, but there's also force, gene. It just raises so many questions. Like, how can we build knowledge on these things if we can't even see them? It's like we're getting a glimpse into the very bedrock of how scientific thought works.
You've got it. That's exactly it.
Mm-hmm.
So maybe we should start by laying down some groundwork here. What are these theoretical terms exactly?
Mm-hmm.
The Stanford Encyclopedia, they give us two main characteristics to think about. The first one, it's that they often point to things that are, beyond our ability to directly observe them. Think about those examples we've been talking about. Electrons, those gravitational forces, genes. We don't experience them directly through our senses the way we do with, say, a table or a tree. We can't see them, touch them, smell them, right?
Right. They're outside of our immediate reach through our senses.
Exactly. Now, the second thing about these theoretical terms, and this is where it gets really interesting, is that their meaning is deeply connected to the scientific theory where they're used. Like, take force in Newtonian physics. We all have this everyday idea of force, right? A push or a pull. Mm-hmm. But in physics, it's much more precise. Its meaning comes from Newton's laws of motion and those related principles, like the law of universal gravitation.
So it's not just about them being invisible or intangible, but their definition itself comes from the theory. It's embedded right in the framework. It's like the theory gives them their substance.
Yes. Exactly. That's it. So our mission today, our deep dive, is to really unpack these two ideas. We're going to explore the whole messiness that comes up when we try to draw a neat line between theoretical and observable. And for you, especially as a philosopher, I think we'll get into some truly deep philosophical waters when we talk about how these theoretical terms gain meaning and how they refer to anything at all.
Okay, that sounds great. Let's get into it. So that first characteristic, reference to non-observable entities,
right,
seems simple enough at first glance, but the Stanford article, it hints at a bit of a difference between how a philosopher might view observability versus a physicist.
That's super important to pick up on. It's subtle, but it makes a big difference. Traditionally, philosophers, they take a very strict view of what counts as observable.
Strict how?
Well, to a philosopher, when you say something is observable, you usually mean that it's something you can perceive directly with your senses, like seeing the blue color of the sky, feeling how hard a rock is, or sensing that ice is colder than, say, a glass of water.
Okay, so we're talking pure sensory data, nothing more. No instruments, no inferences, just direct input from the senses.
Right. And Carnap, who's a key figure in all of this, he was very specific. He said, direct perception can't rely on any instruments or involve any inferential steps. Like, think about how we measure temperature. We use the thermometer, right?
Yeah.
So a philosopher, they might say, well, all you're really observing directly is the level of mercury in that little glass tube, the actual temperature. That's something you're figuring out, inferring based on that observation and your understanding of how thermometers work.
Yeah, that makes sense.
Yeah.
So if we go by that strict definition, then a huge amount of what scientists work with would fall into the category of non-observable, right?
Absolutely. I mean, we've been talking about electrons, molecules, gravitational forces, genes. From a philosopher's perspective, all those would be theoretical. We're not out there directly seeing them doing their thing.
But a physicist, a working physicist, they have a more practical view, don't they?
They totally do. Much more pragmatic. For a physicist, observable often includes anything that you can measure directly, or at least in a simple, straightforward way.
Even if you need instruments to do it.
Right. Exactly. It's less about that pure, unmediated sensory experience that philosophers focus on, and more about having reliable ways to measure things. So things like temperature, pressure, the intensity of an electric current, those are often considered observable because we have pretty well-established methods for measuring them.
Okay, so there's that difference in perspective right from the start. Now, what's interesting is that even Carnap, who was all about that narrow philosophical sense of observation,
Right.
he admitted that the boundary isn't always so clear-cut. Like, he talked about a continuum of degrees of observability.
Yeah.
So maybe where we decide to draw the line depends on what we're focusing on, or maybe even some kind of agreement we've made.
That's a really, really important point, this idea of a continuum. It suggests that maybe that clean division between theory and observation that we started with, maybe it's more of a blurry gradient than a sharp line.
Right. Okay, so let's move on to that second characteristic of theoretical terms then.
Yeah.
The whole idea of semantic dependence upon a scientific theory. Now that sounds a bit more abstract.
It is. It's a bit more conceptual, right up a philosopher's alley.
Yeah.
It's this idea that the meaning of a scientific term, it doesn't exist all on its own. Like, it's not just inherent to the word itself. Its meaning. It comes from how it's integrated into a whole scientific theory. It's given meaning by the context of that theory.
So the theory provides the background, the framework, that gives the term its specific meaning, right? It's like the theory is the environment where that term makes sense scientifically.
That's it. That's a great way to put it. Let's think about force again, that word force. In science, its meaning is inseparable from Newton's laws. You can't really grasp what force means in a physics context without understanding those laws, like the relationship between force, mass, and acceleration. Our methods for measuring force, making sense of it, quantifying it, they all depend on those fundamental principles of classical mechanics.
Okay, I think I see what you're saying. It's not enough to just observe some phenomenon. We need the theory. The theory gives us the conceptual structure to tell us what that phenomenon is, how it fits into the bigger scientific picture.
Exactly. That's exactly right. And this isn't some brand new idea either. The Stanford Encyclopedia, they point to thinkers like Duhem and Poincaré who were advocating for this kind of view way back when. Duhem, he's famous for arguing that you can't really test a single scientific hypothesis in isolation, because its meaning, what it even means, is tangled up with the whole theoretical web it's a part of. And Poincaré, he even suggested that some scientific statements only really gain meaning because we've adopted certain conventions within a particular theory.
So our conventions, our agreements about how we use language, those can actually shape the meaning of scientific terms.
That's the idea.
That's a deeply philosophical concept. It makes me think of all those discussions about, the social construction of knowledge and how our shared understandings shape what we consider to be true.
Yeah, totally. And Feyerabend, he was another philosopher of science, he put this idea very directly in his work. He said that just like a term's meaning depends on being part of a theory, the content of a whole theory, and therefore the meaning of all the descriptive terms in it depends on its empirical consequences. And also, he said, it depends on what other alternative theories are out there that we might consider. So he's basically saying, once you accept that meaning is contextual, there's no logical reason to limit it to just one single theory considered all by itself.
So the meaning of a term, it can evolve, it can be refined. Maybe it changes depending on the whole scientific landscape and all the competing ideas that are out there.
Yeah, that's the implication. Now, those early thinkers, they articulated this whole view of contextual meaning in ways that were, well, a little less formal.
Yeah.
But later on, there have been these attempts to formalize it. Formal accounts of how theoretical terms work, their semantics. They try to translate this idea, contextual meaning, into more rigorous frameworks. We'll get into some of those later. But one thing to keep in mind is that those formal accounts often work with really well-defined axiomatic theories like the classic examples from physics you see in textbooks. But theoretical terms, they're also used in fields that aren't so neatly structured.
Like what?
Well, like evolutionary biology.
Evolutionary biology. So how does this semantic dependence, how does that play out in a field like that?
Good question. Think about the concept of homology in evolutionary biology. It's this idea that similarities in structures between different species, Those similarities come from a common ancestor. Now, evolutionary biology, it's not axiomatized in the same way as, say, classical mechanics, right?
Mm-hmm.
But it still has core principles, theoretical propositions.
Yeah.
Like, we have this idea that two DNA sequences are homologous if they descended from a common ancestral sequence, and that the likelihood of homology is connected to the number and types of mutations that separate those sequences.
Oh.
Those theoretical ideas, they're essential for figuring out what counts as homology. They give the term its meaning, its specific biological meaning within that framework.
So even in a less formally structured science,
Yeah.
the meaning of a key term is still deeply rooted in the overall theoretical framework.
Yes, exactly. And that's a perfect illustration. Now, the Stanford article, it goes on to look at some criticisms and refinements of this theory-observation distinction. I mean, with all the complexities we've already been talking about, it's not surprising that this distinction has been challenged.
Right. So what are some of the main criticisms? What makes this distinction so tricky?
Well, one of the most obvious ones is how technology, new technologies, they keep expanding what we're able to observe. Things like electrons, alpha particles.
Those were once thought to be solidly in the realm of the unobservable, purely theoretical.
Yeah.
But now we can actually detect them, study them, using instruments like cloud chambers, electron microscopes.
So what was once theoretical can become something we can get empirical evidence about. Just because we have new tools, that definitely blurs the lines.
It totally does. And then there's this, well, almost counterintuitive consequence if we stick to that strict definition of observation.
The one that excludes instruments.
Right. If we hold on to that, it means technically we don't actually observe things even when we're wearing glasses, which is a bit odd, right? It doesn't really match up with our everyday understanding of what it means to observe something.
Yeah. I put on my glasses and I can suddenly see the details of a painting more clearly. It feels strange to say, well, I didn't really observe it.
Exactly. It just doesn't feel right. Another challenge comes from the fact that we seem to be using the same basic concepts like spatial and temporal relations, even the idea of color, to talk about both macroscopic objects, the ones we can see, and these submicroscopic things that are supposed to be unobservable. Like in Newton's early theory of light, he talked about these corpuscles of light and even assigned them colors.
So when we talk about the distance between two galaxies and the distance between two quarks, are we really using distance in the same fundamental way?
You got it. That's the crux of the problem. Now, the Stanford Encyclopedia, they highlight that from a Carnapian perspective, there are some ways to respond to these criticisms.
Okay, how so?
Well, about instruments, Carnap was very clear. He said that the philosopher's definition of observation, it intentionally leaves out instruments. As for the glasses thing, he was willing to be a bit more flexible. He suggested that maybe observability depends on the observer's abilities, what they're capable of. He even used colorblindness as an example to illustrate this point.
So, like, observability becomes relative to the observer. It's not just an absolute property of the thing itself.
That's the idea. And it's really important to remember that for Carnap, his main goal wasn't to create a perfect mirror of how we talk about observation in everyday language, or even in science. He wanted to come up with a distinction that was useful for analyzing scientific theories logically. He knew there wasn't a perfect sharp line. He acknowledged that it's more of a continuum.
So for him, this whole theory-observation distinction was more of a tool for doing logic and philosophy of science than about reflecting some kind of absolute division in reality.
That's a very, very insightful way to put it, yeah. Now, Putnam, he brought up a more specific objection. About applying observation concepts to those tiny submicroscopic particles. And one way to respond to that, maybe from a Carnapian view, is to introduce different predicates, different words, essentially.
Like what?
Well, in a formal language, you could have red 1 for macroscopic objects, the ones we can see, and red 2 for submicroscopic things that interact with our detectors in a way that makes us call them red.
So, like, we create different categories of terms to handle those different levels of reality, even though we might use the same word in everyday language.
Something like that.
Yeah.
And then, of course, we have this super influential idea, the theory-ladenness of observation.
Oh, yeah. I've come across that before. Theory-ladenness.
Right. So how does that challenge the theory-observation distinction?
Well, as I understand it, it's this idea that our observations, they aren't neutral. They're not independent of the theories we already hold. It's like our theories influence what we see, how we interpret what we see.
You got it. Hansen, He gave this really famous example. He argued that when Tycho Brahe and Johannes Kepler looked at the sunrise, they were literally seeing different things because their astronomical theories were so different. And Feyerabend, he took it even further. He suggested that in a really deep way, all terms are theoretical. And Kuhn, he was a bit more nuanced, but he also stressed that our theoretical frameworks shape what we notice and how we make sense of it.
So it's not just that our interpretation of what we see is influenced by theory, but the very act of seeing itself. Wow, that's a pretty radical idea.
Yeah, it is. It directly challenges a common assumption in many formal accounts of theoretical terms, that there are these observation terms and their meaning is totally independent of the theories they're supposed to be explaining. So yeah, this whole theory-ladenness debate is a big deal in philosophy of science.
Okay, so a lot of fundamental challenges. What about attempts to, I don't know, maybe refine the theory-observation distinction, salvage it, or maybe come up with something totally new?
Right. Well, there have been some really important attempts to do just that. One influential approach is to relativize the distinction, make it relative to a specific scientific theory.
Okay, how would that work?
So you would say a term is T-theoretical, where T stands for a particular theory, if that term was first introduced by that theory T. And then you'd have O terms. Those are your observational terms. And those are the ones that were already around and understood before theory T came along.
So the theoreticalness of a term, it's tied to its origin story within a specific scientific framework and how it relates to those pre-existing concepts.
Exactly. And Snead, he worked on this structuralist view of scientific theories. And he proposed a more formal way to do this.
Okay.
He said a term, let's call it T, is T-theoretical, again, T for a theory. If any method we have for figuring out what it refers to, its extension relies on at least one axiom of that theory, T.
So it's not just about when the term was introduced, but also whether our way of understanding what it actually picks out in the world depends on the theory being true, or at least on us accepting those axioms.
That's it, exactly. He explains it like this. A method rests upon an axiom if, hypothetically, if that axiom turned out to be false, or maybe we couldn't determine whether it's true or false, then our methods would be invalid. We couldn't use it anymore. And he gives the example of classical particle mechanics, CPM. So all our methods for figuring out force, they rely on Newton's laws, or on specific force laws that come from them. So force is CPM theoretical. But when it comes to measuring distances in space, well, that doesn't inherently depend on CPM.
So spatial distance, it's CPM non-theoretical, at least in that specific context.
Yes, exactly. Now mass, that one's a bit trickier. Its measurement can involve classical collision mechanics, but the structuralists, they argued you can reduce it to CPM. So it ended up being CPM theoretical too, from their point of view.
So whether a term is theoretical or not, that can even be relative to the specific theory we're dealing with.
Yeah, absolutely. It's all about the context. And Snead's original formulation, it gets even more complicated, involving set theory and this idea of intended applications of a theory, which is the key part of structuralism. And even within that school of thought, there's debate about how to pin down this idea of theoreticity in a precise way.
Yeah.
Kuhn, he was also in favor of this kind of double relativization to a specific theory and to its particular domains of application.
So it seems like this idea of a fixed universal theory observation distinction, it's kind of been replaced by more flexible, context-dependent views.
I think that's a fair assessment, yeah. Now, here's something interesting. The Stanford Encyclopedia, they point out that Snead's criterion, it also hints at a possible way to go back to a more global, non-relativized distinction.
Really? How?
Well, you could say that a term is theoretical, simply theoretical, if all the methods we have for determining its extension depend on some axiom of some theory. So it doesn't matter which theory, as long as there's always some theory involved. And a non-theoretical term would be one where we have at least one method for figuring out its extension that doesn't depend on any theoretical axiom.
Okay, I see. So even when we're trying to come up with a universal distinction, we still can't escape this fundamental role that theories play in how we define and understand our terms. It always seems to come back to the theory.
Yeah, it does. Now, the article then moves on to what it calls two problems of theoretical terms. And these get at the heart of the philosophical difficulties with these terms.
Okay, what are those two big problems?
The first one is about theoretical entities themselves. It's the challenge of giving a good, satisfactory explanation for their meaning and how they refer to anything at all.
Like, how can we talk about quarks or black holes and actually be referring to something? And what do we even mean when we use those words?
Exactly. Those are the big questions. And this issue, it's deeply tied up with the whole debate about scientific realism.
Ah, yes. The question of whether those theoretical entities, whether they actually exist out there in the world, independent of our minds, independent of our theories?
Right. Exactly. So you have scientific realists. They believe that those theoretical entities and the natural kinds they belong to, they really exist. They're not just in our heads.
Mm-hmm.
And then you have instrumentalists. They often see theoretical entities more as useful tools, like fictions that help us make predictions. They don't necessarily say those entities really exist.
Mm-hmm.
And then you have more nuanced positions. Carnap, for example, he tried to stay neutral on this whole realism versus anti-realism debate. He suggested that when we talk about theoretical entities, we could understand that talk as actually being about mathematical entities.
Mathematical entities. So an electron, for Carnap, it wasn't necessarily a little particle with physical properties, but more like a set of mathematical relationships that helps us organize our observations.
That's a pretty good way to sum it up.
Yeah.
It's what the article calls his Pythagorean view. He thought of theoretical entities as having this mathematical structure that gets connected to the empirical world through axioms and rules of correspondence.
Okay.
Now, within these different metaphysical stances, you also have different accounts of how reference and meaning actually work for those theoretical terms. The Stanford article, it highlights three main ones: descriptivist accounts, causal accounts, sometimes called causal historical, and hybrid accounts.
Okay, let's break those down a bit. So descriptivist accounts, what's the main idea there?
The basic idea is this. A theoretical term, it refers to whatever entity uniquely fits a certain description. So like electron would refer to that subatomic particle with a particular mass and charge. Our understanding of the term, it's tied to that cluster of properties, that description.
So the meaning of the term is basically just all those properties that we currently think it has.
Yeah, that's the gist of it. But it runs into problems when you look at the history of science.
How so?
Well, if our descriptions of theoretical entities change, maybe even change radically across different theories, it makes you wonder if scientists using the same term at different times were even talking about the same thing.
Yeah, like the model of the electron, how it evolved from Rutherford's model to Bohr's model, right?
Right, exactly. Were they talking about the same entity, just with different descriptions? Or were they completely different theoretical constructs? It raises this whole problem of incommensurability between theories. And what happens if a key part of our current description of a theoretical entity turns out to be wrong? According to a future theory, I mean. Does that mean that in the earlier theory, the term didn't actually refer to anything?
That would be a problem, wouldn't it? Because it would mean that past scientists, even if their theories were successful in some ways, they might have been talking about nothing at all.
Right. Exactly. And that's why descriptivists, they often have to introduce these ideas of weighting parts of a description differently or focusing on essential properties to try to hold on to reference across those theory changes.
Okay. What about causal accounts? Those causal historical accounts, how do they work?
Those are interesting. They come from Kripke's work, famously. The basic idea is that a term gets its reference through an initial baptism.
Baptism, like naming ceremony.
Yes, sort of. Like at some point, someone or maybe a group of people, they identify something, maybe through its effects, and they give it a name. That's the baptism. And from then on, that term refers to that thing. And the reference gets passed down through all these causal chains of communication. So electron refers to whatever it was that was initially identified and labeled as an electron, and that reference gets passed down through the scientific community.
So it's less about the description and more about the historical origin of the term and its initial connection to the world.
Right, exactly. But this view can feel a bit odd, especially when you think about science education, because we usually focus on the current understanding of those concepts, not their historical introduction.
Yeah.
And it doesn't fully explain the meaning of those terms. Just having that causal link back to the original naming event doesn't tell us everything we know about an entity or how we should think about it.
Or it doesn't give you the full content of the concept.
Exactly. Even in philosophy of language more generally, this account has been criticized because it doesn't really deal with the descriptive stuff that's part of meaning.
So it might explain how a term gets its initial grip on reality, so to speak, but it doesn't fully explain how we come to understand what that term signifies, all the details, the nuances.
Exactly.
Yeah.
Right. And that's where those hybrid accounts come in. They try to combine the good parts of both descriptivist and causal accounts. Psillos, for example, he argues that a term refers if the entity, that thing it's supposed to be referring to, satisfies what he calls the core causal description associated with that term.
Core causal description.
Yeah, so it's this idea that two terms refer to the same entity if their supposed reference, those things out in the world, play the same fundamental causal roles, and their core causal descriptions share kind-constitutive properties.
Kind-constitutive properties. What are those?
Those are the properties that are essential to the kind of thing it is. Like what makes an electron an electron? It's a combination of what the entity does, its causal role, and its fundamental nature, those kind-constitutive properties.
Okay, I see. So it's this blend of the causal stuff, how it interacts with the world, and the descriptive stuff, what kind of thing it is.
That's the idea. And this view, it fits more closely with how scientists actually use and understand theoretical terms. And it aims for a more stable notion of reference, one that can handle some degree of theory change, as long as those core causal roles and kind-constitutive properties stay the same. The tricky part, of course, is figuring out what exactly counts as a kind-constitutive property, defining that precisely.
Yeah, that sounds tricky. So it seems like this problem of theoretical entities, it's really deep. It's a mix of metaphysics, semantics, the whole history of scientific thought, all these things.
It really is.
Now, what about that second problem, the problem of theoretical functions and relations? How is that different?
That one, it comes specifically from that idea we talked about earlier, the whole semantic dependence thing.
Right, that the meaning of a term depends on the theory it's part of.
Exactly. Remember Sneed's criterion. He said a term is T-theoretical, T for a theory. If any way we have of figuring out what it refers to depends on at least one axiom of that theory.
Yeah, I remember that. So how does that create a problem for theoretical functions and relations, things like force or temperature?
Well, the problem is this. If the only way, or maybe just the primary way, that we can measure or understand a theoretical function or relation depends on the very axioms of the theory that includes that term, we end up in a kind of circle.
A circle.
Yeah, like to measure force, we rely on Newton's laws. But the truth of Newton's laws, that depends on what force actually is. It's like we need to know what the theoretical term refers to, its extension, to check if the axioms are true. But we also need to accept the axioms to even determine what the term refers to in the first place.
Yeah, that does sound circular. It's like trying to define a word by using a sentence where the meaning of that word is essential to understanding the sentence.
Exactly. You got it.
So, if our understanding of the key terms is already baked into the theory, how can we independently test whether the theory is true or not?
That's the problem.
Okay.
And Sneed, he called this the problem of theoretical terms. And he mostly saw it as an epistemological problem. How can we get independent evidence for the truth of a theory when it's applied to specific cases? But it also had this big semantic side to it. Because if the meaning of a term is tied to the methods we use to figure out what it refers to, then our understanding of those T-theoretical terms, it comes from the theory's axioms. But in standard semantics, the kind that focuses on truth conditions, it's often assumed that the truth of the axioms depends on the meanings of the terms that are already in them. So there's this potential mismatch in the order of how we come to understand these concepts.
So this semantic dependence, it creates this hurdle for independently testing our theories. It's like we're trapped in the theory's own web of meaning.
You got it. That's the challenge. And this difficulty, it's one of the things that has led to the development of all these alternative ways of understanding how theoretical terms get their meaning. And that brings us to the next big section in the Stanford article, the formal accounts.
Formal accounts.
Yeah, this is where philosophers and logicians, they get really serious about trying to create more rigorous and precise ways to tackle these tricky issues.
Using logic and formal systems.
Exactly.
Okay, so where do we start with these formal accounts?
Well, a good place to start is with the Ramsey sentence. Frank Ramsey, he was this brilliant philosopher, mathematician, and he came up with this way to rephrase a scientific theory.
How?
Basically, you replace all the theoretical terms with variables. And then you use these things called existential quantifiers to bind those variables.
Existential quantifiers. That sounds a bit technical.
It is, but I think we can unpack it. Imagine a theory. Let's call it TC.
TC.
And let's say it has two types of vocabulary. Observational terms, VOL. Those are the terms we understand pretty well through experience. And in theoretical terms, VT, those are the tricky ones.
Right.
The Ramsey sentence of TC, we write it as TCR, it's created by taking all the axioms of TC and putting them together. But instead of using those specific theoretical terms like electron or force, we swap them out with variables. And those variables, they stand for a property, a relation, or a function, depending on what the term is.
Okay.
And then we say that there exists some way to interpret those variables so that when we plug in those interpretations, along with our understanding of those observational terms, it makes the original theory, TC, true.
So instead of saying something like electrons exist and they have these specific properties, the Ramsey sentence says, there is something that has some set of properties and is related to the things we can observe in certain ways, and if that's true, then our theory holds together.